Okay, so last time we talked about asymptotic freeness between unitary matrices, unitary random matrices, and deterministic matrices. And in particular, we looked at a situation where I take, let's say, two deterministic matrices and I rotate one of them by a high unitary. And we calculated that this in a limit converges to something of which we recognize that this describes a free situation. But actually, I mean, it was not as in the Gaussian case, where we recognize a situation in a limit, which clearly is more or less the moment cumulant formula, or a description in terms of moments or cumulants of free variables, which we recognize immediately. But last time it was more a formula, which is not so easy to see what it really means, and we just used the definition of freeness to show that this formula really describes something which is free. And I want to make maybe a remark on this. Really, I mean, of course we know for this situation how the formula should look like in terms of non-crossing partitions, and we should compare those two. And I want to make a few remarks on this. Okay, so what we saw last time, so was our formula. Maybe I can start, but I will say what it means. So this says that was the formula which we got in the limit of our random matrices, where we had two sequences and one of them was located by U. So this says that two sets, let's say A1 up to AM and B1 up to BM, we have following formula. For mixed moments. So namely we have phi of A1, B1, A2, B2, AM, BM, also an alternative product with the A's and the B's, and the A's are free from the B's. And what we got last time in the limit was a formula which we recognized to be a formula for free variables. So this means for free variables we should have this formula which we got last time, and this formula was summing over permutation, not over non-crossing partition, but it was summing over two elements from Sm, the permutation group on M elements. So here we are multiplying MAs and MBs. Okay, but we are not summing over all of them, but only those which satisfy a kind of condition. And this condition was in terms of this absolute value. So you remember the absolute value was M minus the number of cycles, and we saw that this is essentially a distance, or that this gives an absolute value. So it's, in particular, it satisfies the triangle inequality. And the condition was that alpha minus 1 beta, absolute value of this, plus absolute value of alpha, plus absolute value of beta to the minus 1. And then we multiply with gamma. And gamma, as usual, is this long cycle which moves 1 to 2, 2 to 3, and so on, up to m minus 1 to m, and then m to 1. And the sum of all those absolute values of those guys is equal to m minus 1. Okay, so we consider such pairs of alpha betas, and then they make a contribution, and we have a contribution of the moments of the alphas, of the A's, and they go with the alpha. So I have phi alpha of A1, so on, up to AM. So this is a product of the moments of the A's, and which product? The product according to the cycle decomposition of alpha. For each cycle alpha, I have a moment where I multiply the A's, which correspond to the indices appearing in the cycle. Okay, and then I get also a contribution of the B's, and there I have the moments where I take this permutation beta minus 1 and gamma. B minus 1, so on, up to M. Okay. And then we also had a factor which came from the leading order of the Wigner function, which was phi of alpha beta to the minus 1. mean, this phi we don't really know. I just told you this. There's a leading order and Weingarten function. It's not one. It's more complicated. No? So it's something. Okay, so we have something which tells us that the mixed moment of A's and B's are given in terms of the moment of the A's and the moment of the B's as it should be for free variables. But of course, freeness means there's a very specific rule. And I mean, this doesn't really look like the specific rules we know. But we check that this really describes a free situation. And maybe we should compare it with the formula for free variables. So what do we know? I mean, how would we describe such a product? So on the other hand, our combinatorial cumulant machinery we know also a formula to name the unit. Yeah, write it in the following. So we have 5 A1 B1 up to AN BM. So if I want to calculate such a mixed moment, how do I do this? Okay, I write it as a sum over non-crossing partitions of all those elements. Then because the A's and the B's are free, we know that it decomposes into a non-crossing partition of the A's and a non-crossing partition of the B's, but they must fit together in the way that they are together non-crossing partition, and this means that the part for the B must be less than the Rivera's complement of this, and if I do the summation, I get the moment of this. So that's something we already did a few times, but so in principle, we have a priori a formula which involves the moment of one of them and the cumulant of the other. So we have a summing over non-crossing partitions of M. Then I get the cumulants of the A's up to AM. Okay, and then in principle I would get the cumulants of the B, but I'm summing over all non-crossing partitions which are less than the Rivera's complement of this, and this gives me the moment. So here I get the moment of the B's, but at Rivera's complement of pi. Okay, so that's what we get directly, but now here we have a formula where we don't want cumulants. So this means we should also go over here from those cumulants to the moments. And of course we know how to do this by the moment cumulant formula, or the other way around. So we express the cumulants in terms of the moment, where we also have to invoke the Möbius function. Okay, so we can express this, and of course so we have to sum again over some non-crossing partitions to do this, and so you see we will get two things over which we have to sum, but here we are summing the non-crossing partitions. So we are summing over pi, and now for expressing this I'm summing also over sigma in the non-crossing partitions. Okay, if I want to express the kappa pi in terms of the moment, I have to sum over all sigmas which are less than pi. So I'm summing here over sigma which are less than pi, and then I can write this as phi sigma of A1 AM, and this just stays as it is. It's the phi of the complement of pi B1 up to BM. Okay, and of course here I also need the Möbius function. So I mean if I go from moments to cumulants, all the coefficients are 1, but if I go backwards, I get the Möbius function, so I have also here the Möbius function from sigma to pi. So this here is the sum over this, and this summed over sigma, which are less than pi. And now you see, I mean, this formula looks, from a structural point of view, very similar. We are summing over two guys in the non-crossing partitions. Here's a computation group. Okay, they satisfy some condition. And we have the contribution, the moment of the A's, the moment of the B's, and we have some additional function here, which there we don't really know what it is, but here we know very precisely what it is. It's the Möbius function. So it suggests that this guy here actually should be related to the Möbius function. And actually, that this formula and this formula must give the same result. I mean, suggests that actually the terms appearing there should not, they should be in bijection. So I mean, of course, it's just saying the sum there is the same as the sum here, but because we have this for all instances, I mean, this really suggests that, I mean, each term here should correspond to a term here. And this is actually the case. So, we have an embedding of the permutation group in the non-crossing partitions. The other way. We have the non-crossing partitions are embedded in the permutation group. So here we are summing over special pairs of permutations which correspond to non-crossing partitions. I mean, before we also, in the Gaussian case, we also somehow we worked with a permutation group, but then it was just that we considered pairings embedded in the permutation group. But here we see that actually this is too much more general. I mean, any non-crossing partition can be found in the permutation group. So, see here, suggests we have an objective correspondence between the terms which appear both formulas terms. And this is really true. I mean, of course, one has to prove this. I'm not going to do this. I just want to say one or two more. So this is true. And so what we have here in particular, what is behind this, particular, we have that the non-crossing partitions of m elements can be embedded in Sm permutation groups in a nice way. So there's a lot of structure to serve. So NC of M can be embedded in the permutation group of n elements as, let's say I take S, NC of gamma, which I will define in a moment. So this is a subset of Sm, but this is isomorphic to NC of M, not only as a set, but one can also put a coset structure here, and then it's the same. But here let me just tell you how I describe the partition, the permutations which are correspondent to the non-crossing partitions. So where, so this S, NC of gamma, it's just a small crossing, and gamma means essentially it's related to this cycle gamma. So the cycle gamma, of course, is just all the numbers, 1 up to n. So this corresponds to the permutations in Sm, for which the absolute value of alpha plus alpha to the minus 1 gamma is equal to m minus 1. Okay. And if you think a little bit about this, in particular, if you remember, we can also introduce a difference. So we have an absolute value, and this absolute value essentially tells us how far away elements in the computation group are away from the identity element. And of course, you can use this for defining a distance by just taking the absolute value of beta and alpha minus 1. So this is a distance in the computation group between two permutations, which essentially tells you how many transpositions you need to go from one to the other. Because the absolute value was counting the number of transpositions which you need to write these. Okay, and in this language, this here tells you exactly that this alpha lies on a geodesic from the identity element to this gamma. So this is exactly, instead of a triangle inequality, I mean this is a distance from the identity, I should say this is the distance from the identity element to gamma, because gamma has one cycle, and this here is the distance from the identity element to alpha, and this here is the distance from from what to what? From alpha to gamma. So you see, I mean, in general, I have a triangle inequality that this is less than this plus this, but here I have equality, and this just means I'm having a geodesic going from here to here, and alpha is a geodesic there. Oh, so this, to say alpha is a geodesic from the identity element, the permutation to gamma. For this distance here. Good. Okay. And if you think a little bit more about this, here you have two guys. So each of them must be in this set, and that you have this property tells you that both of them lie on the same geodesic. So this means that alpha, that beta comes after alpha on the same geodesic. And this corresponds. This is actually this allows you to put also a partial order of this, and this corresponds to this. So you can really check that really you can transfer all properties from the permutation group to this, and you really have a one-to-one correspondence. Good. So in assignments, you should look a little bit on this embedding, not really proving things, but at some examples really look what this really means. So this embedding of NC3 or NC4 in S3 and S4, maybe really check what this means. Good. Okay, but so I don't want to say more about this, but it's just saying that actually what we get here looks quite different from what we usually have, but in the end it's the same. And it really corresponds to the fact that we have a very nice embedding of non-crossing partitions in communication groups. And actually this was done by Philip Young in 1997. Good, so same thing. Good. Okay, now that's about the unitary random matrices and the Gaussian. So those are the nicest random matrices transformers which we have. And for them, the calculations are, if you want to remove moments, are really very nice. In particular, we derive formulas where even for finite n, everything only depended on the moments. So you also include deterministic matrices, then mixed moments in the Gaussian or the unitaries, and these deterministic matrices, even for finite n, depends only on the moments. Okay, so this is really the fact because we have a unitary symmetry here. But now I want just to make a remark on that actually, asymptotic freeness results, we have also in more general situations where maybe we don't really have this nice unitary symmetry, but still, in the limit, things are very nice. And one canonical and important example is a generalization of the Gaussian random matrices. So I want to make a few remarks on this, because those are the so-called Wigner matrices, and they are also very important also in applications. And there the question about asymptotic freeness is a bit more tricky, but in the end it's true. So that's the main thing which I want to say here. I'm not really going to prove things, but just give you some ideas. Okay, so our basic random matrix model up to now was, let's say, the GUE. And what is the GUE? This means we have a random matrix which has some symmetry, but apart from this, I have IID entries. So this means identically independent and identically distributed entries. Okay. So the entries are independent up to symmetry, of course, up to the symmetry that I want symmetry matrix. But apart from this, they are independent and they have the same distribution, but actually this distribution was chosen in a very specific way, namely it was a Gaussian distribution. So, Gaussian distribution for the entries. Okay, and of course one can generalize this, and it turns out maybe improve, you see that actually the important thing for the Wigner semicircle, for example, is the independence and the identical distribution, okay? But that this distribution is a Gaussian, that's not really so important. Of course, it made our calculations very straightforward and elegant, but actually you can do similar calculations if you take here another distribution. Okay, so there is a kind of generalization of this ensemble, where you keep this here, but you replace Gauss by an arbitrary distribution. So there exists the generalization. This, and those guys are usually called Wigner matrices. I mean, actually, when Wigner introduced random matrices, he did not from the beginning look at Gaussian ones, but he looked on the Wigner matrix where the entry distribution was maybe not normal, but something else. Okay. So this here means we still have ID up to symmetry. The entries of the matrix are independent and they have all the same distribution, but this distribution is now not a Gauss, but it can be something arbitrary. And of course this should be fixed in the beginning, in particular if we send n to infinity, then of course we fix a distribution mu and then we look at a sequence of matrices which all have, the entries have all this distribution mu. So with arbitrary distribution for the entries. Okay, and now it turns out, and it's well known from the random matrix literature, that these Wigner matrices behave in many aspects like the GUE. In particular, if I'm looking on the asymptotic eigenvalue distribution of them, they still converge to the semicircle. So, okay, I don't need the Gaussian entries for this. And of course, in our context, it's important if this similarity between the Gaussian matrices and the Wigner matrices also goes to asymptotic freeness questions. I mean, this is not so clear a priori, but it turns out that this is the case. But so the important case is asymptotic freeness. So I don't want to say a few remarks about this, but so maybe let me just define rigorously the Wigner random matrix. So let mu be fixed, so mu be probability on R. And let's say I'm looking now on real matrices. Of course, in the Gaussian case, the GUE was actually complex ones. But let me do here the real case. So the Gaussian complex case also was usually more or less the same. Okay. And so we fix a distribution on R, and then we say the corresponding to this mu, the corresponding Wigner random matrix. Wigner random matrix. So this is of the form. Yeah, and again, I mean, I have AN. I have for each n, I have such a guy. So AN is an n by n matrix, and we take a normalization, and of course the normalization is the same as for Gaussian, so we have a 1 over square root of n, and then we have entries Aij going from 1 up to n, so it's n by n matrix, where the Aij's are of course IID up to the symmetry, and each of them the distribution is this mu. So there we have the Aij apart from the symmetry, so this means that all the guys above the diagonal are independent and identically distributed, in this case real random variables, classical random variables, with the given distribution mu. And of course, then we have the symmetry. So we want that our matrix is self-adjoint, which means, of course, that the entry Aij has to be the same as Aj. I mean, in real case, so I don't need the bar. Good. Okay, so that's my Wigner matrix. And now the first theorem about this is actually the theorem of Wigner, that this converges in distribution to a semicircle. So that's a theorem which I formulated more or less for the Gaussian case, but Wigner actually proved it for things like this. So here's the theorem. Was essentially the theorem of Wigner. And okay, so I mean all those theorems can be done in a very general situation. If you do analytic approaches, then you only need maybe the second moment for the distribution mu. If, as we do it, we do a combinatorial approach by looking at moments, then of course we need all moments of the entries. So let's assume this here. But I mean there are generalizations of this theorem. So assume that all moments of mu exist. And of course we also need, in our combinatorial approach, that the first moment is 0. Actually in analytic approach one can even get rid of this. But so let us assume this in our situation. So we assume that first moment is 0. Okay, and then we consider a sequence of such corresponding Wigner random matrices, and then the statement is in distribution, of course, as usual with respect to the expectation and the trace, this converges to a semicircular distribution. And running over all natural numbers, the sequence of corresponding Wigner matrices. Let me state it here. Okay, so let AN be a sequence of corresponding Wigner matrices, and then we claim distribution, this sequence converges to a semicircular element. So S. As usual, semicircular. Circular element. Good. Okay, and I want to give you a sketch of the proof of this, because I mean now, of course, it's getting a bit more complicated because we don't have the Wig formula for the entries anymore. I mean, the Wig formula made things very smoothly, and we had very explicit formulas. Here, of course, I mean, for finite n, we will get formulas which are not so nice, and the point will be to see that in the limit, only the leading order terms survive, and those are the same terms as in the Gaussian case. And the other terms have to go to 0. The other terms we don't really know so well, but I mean, we have enough control to see that they go to 0. And so, somehow a sketch of the proof, not all the details, but ideas. Yeah, of course, in our combinatorial way, we calculate the moments. I mean, what we're really claiming here is that the moment of this guy converges to the corresponding moment of this guy, which is color line. So we have to calculate the moments. So again, as usual, I take the nth moment of my matrix, and write this again in terms of the entries. So I have some factors of n. I mean, one n comes from that I have the normalized trace, and then I have a factor square root of n for each of the ANs, so I get it m over 2 times. So 1 plus 2. And then I have to sum over all indices coming from matrix multiplication and trace. And of course I'm taking the expectation of those guys. So I have the product of m factors. So I have I1, I2, A2, I3, IM, I1. So this is the simplest case. Only you just have one random matrix, then you just take the matrix multiplication, which happens here, and we take the trace, which tells us that the first and the last index are the same, and we have to sum over this, and we have to sum over all possible values of indices here, so which means we are summing over all the multi-indices or functions going from m to n. So we have m indices, and each of them can take all values between multiple. Good, so that's the starting point, and now of course we have to see what are those terms. And as in the Gaussian case, we have to collect terms here into classes which have the same contribution. And of course here again I have a product of variables, some of them are independent and they have all the same distribution. Okay, so if I have the same structure here for different indices i's, of what is independent and what not, then of course I will get the same contribution. Right? So I should collect the terms. Okay, and here we can do this, for example, by collecting terms which have the same kernel of I. I mean, in the Wig formula, actually, it was looking on where do I have the same variable here and here, which means we have to compare the pairs which are here. Here, I mean, it makes more sense to look on the kernel of I. So what I do here is keep what I have here, 1 plus n over 2, and then I split my sum here over all I into possible kernels, which are just permutations of m elements, and then I am summing over the I, which have those as a kernel. So I'm summing first over permutations of m elements, and then I'm summing over the i's, as before. But now under the restriction that the kernel of I is equal to sigma. You see, it's a little bit different as in the other case, because I mean, in the Gaussian case, we came up with permutations which told us which was about the positions of the variables. Here I'm taking the permutations of the i's. And the i's appear always as pairs as the variables, but I mean this is the same as this. So this somehow you just do a thing whether I look on the positions of the a's or whether I look on the indices which show up here. Okay, here it might be more, might be better to do it like this. And again, I still have here the expectation of I1, I2 to I1. And now the crucial point is that this guy here, the value of this depends only on the sigma. Which means that if I have index at I and index at j, for which have the same kernel, then this expression is the same. Because then of course, I mean, what we have to check is what happens with the pairs. So we have to see where the random variables appear again, and this depends, of course, always on this pair. Okay, but if the I and the j are the same, then the pairs are also the same, and which means it gives the same contribution. Okay, so the point is that this depends only on sigma. So maybe I can just note this by E of sigma. Okay, and then of course the usual thing, I mean I'm exchanging essentially those two sums and summing over i's, which have a given kernel is easy. Of course. If I'm fixing the partition and I want to have a multi-index which have its kernel at this partition, this means I can choose an index for the first block, then I can choose an index for the second block. This index only has to be different from the index from the first block, and so on. and I'm summing over all partitions. Each of them gives me this common value for this expectation of the products here, and then I have to sum over the indices which have this common kernel, but this is just counting how many are there. Okay, how many are there? So I mean, for each block of this permutation, I have essentially n choices. I only have to take care that they are different. So for the first block, I have n possibilities. For the next, I have n minus 1, and so on. For the last block, I have n minus the number of blocks plus 1. Okay, because if I have a partition like this, and I want to know how many indices tuples, six tuples do I have, which take on those values, then of course, I mean, this tells me exactly that here and here I must have the same value, so I can put a number here. For this I have n possibilities. Okay, and then on this block I can put a second number, but it must be different from this one. So I have n possibilities. Then on this block, I mean, I have n minus 1 possibilities. Of course, it tells me this and this and this must be the same. So I choose one number, and then you can see it here. And then for this last guy, I can put anything which is different from what I already had before. So for this, I have n minus 2 possibilities. Okay. So essentially, for each block, I have a factor n going down in steps of 1 because I have to take care that they are different for different blocks. But if n goes to infinity, of course, this goes like n to the number of blocks. So then the constraint that they have to be different on different blocks is not really important. Good. Okay. And so what we have to see is essentially this here. And of course now the point is, you see I have here contributions in n. So the contribution in n, what I have here is sigma in Tm, e to the sigma, and I have a contribution which goes with 1 plus m over 2, or minus plus number of blocks of sigma. Okay, now of course the point is that in the limit n going to infinity, only things survive for which this here is exactly 0. Okay, so we should see that first of all in general, this cannot become bigger than 0, and then we have to identify the sigmas for which this is 0. Or okay, this can also be 0. Of course, there will be terms for which this is 0, for which is important at the first moment is equal to 0. But for the guys for which this is not 0, then we have to identify what do we have here. Okay, and for this, it's advantage to encode the information about the sigma in the graph. Okay. So you see, this is getting more complicated than the Wig formula. I mean, the Wig formula is very, very direct and smooth, and it tells us everything directly. But here we have to think a little bit more carefully which sigmas show up here. And the Wig formula directly gives us a summation over non-crossing over pairings. Here we are still summing over all sigmas, and we have to see what survives. And for this, what one is usually doing is that we identify sigma with the graph. Let me call it G sigma as follows. Okay. So the point is, or the problem is, that I mean we have here partitions of the indices, but what we really, the information which is really important are the entries, and they have two indices. So actually, I mean, it's always pairs of indices which are the index of this I. Okay, and this in the graph can be encoded in a very nice way that the i's are vertices, and actually this here corresponds then to the edges. So actually, so what we really have, I mean, if I just have this summation here over all the i's, then you should think of this as, let's say, having a graph where the i's correspond to the vertices, and then these guys here correspond to the edges. I mean, this is the edge I1, I2. So because it goes between I1 and I2. Now this here is AI2, I3, and so on. So the terms which we show up here correspond to the edges, they are getting multiplied, and but we are summing over all those guys here. And the partitions which we have here are partitions of those guys. And we have to control what happens with the edges, because we want to know when are the edges the same or not. Okay, now we have a sigma which identifies some of the i's. So this we are taking now the graph where we identify this. So we identify here what is this via sigma, and then we get another graph where we keep all the edges essentially, but we have this identification. And maybe let me do an example. So let's say sigma is 1, 4, 3 and 6, and 5. So this is a partition of 6 elements. So here I have 6 vertices, so I identify now some of them. And now I'm identifying I1, I2 and I4. So I1, I2 and I4 are now identified. They become a new vertex. I mean, they have the same value. So I have 1 is 2 is 4, let's say. Then I have 3 is 6, and I have 5. So I have identified those vertices. So only 3 different vertices are now left, and I have to put my edges now into this. So I have here the edges 1 goes to 2, but 1 and 2 is here, so this is actually now a loop. Then 2 goes to 3, which is here. 3 goes to 4, so I'm going back, but I'm not drawing this again. So because I already have this connection. Then from 4 I go to 5, from 5 I go to 6, and from 6 I'm going back to 1. So that's the new graph. And of course the edges which I had there correspond now to the edges here. So this here is A1, I1, I2, and now in the case where I1 is equal to I2. Okay, and here at this point, I mean this actually corresponds to 3 of the edges which I had there. So this is A I2, I3, A I3, I4, and A I6, I1. Because they are all the same, because the i's are identical according to this. Okay, and here I have I4, I5, and here I have A of I5, I6. Okay, and so now you see this expectation here is now the product of the variable sitting here. Okay, but you see here if one variable appears only once, like this or this, then of course the expectation, then it's independent of the other guys. And the expectation of the whole product here factorizes, and because the first moment is 0, this will be 0. So this means if I have a graph where some of the variables appear only once under this identification, then this guy here is 0. So this means I only have to look for graphs where each edge corresponds to at least 2 of the guys here. Okay, and actually, then one has to see the leading order, and then it turns out that actually it has to be true that it must correspond exactly to 2, and in leading order, the graph which survives is exactly 3. Okay, so those are things one has to think about a bit, but there are 2 parts. But I mean, it gives you the idea that things are not as easy as for the Gaussian case, because you don't have the big formula, which is a much more prescribed, much more precise description than what we have here in the general case. In particular, here in the general case, we cannot reduce the higher moments of mu to the second order moments. So we will have terms where we have also the fourth moment or the sixth moment of mu showing up. But the point here is to see that in the limit, those guys don't contribute. But they could be more or less quite arbitrary. So for final n, we cannot really control them. But with this argument, one can see in the limit they disappear. Good. Okay, so this is now maybe the sketchy part. I'm not giving more details. I just tell you that for leading order, actually needs in this graph each edge to correspond to 2 aij. Okay, but this is more or less clear. I mean, at least 2, but then of course it should also be clear that exactly 2 is the leading one. Okay, and then in this case, the corresponding graph is a tree. And now to really make the connection with our description in terms of non-crossing pairings, because I mean the sigmas here are not the pairings. I mean the sigmas tell us where the eyes are the same. I mean for the pairing picture, of course we should know at which positions do we have the same variable. But this transition from position to indices actually is in our language given by the Preveras component. So that this is a tree and sigma is the Preveras complement of a non-crossing pairing. And this brings us back to our usual formula. Essentially, I mean, the sum over the sigmas which survive in the limit is actually a sum over non-crossing pairing. Okay, maybe just to make it a little bit clear, give me an example of a thing which survives. So let me take a sigma which survives in the limit, for example, is 1, 5, 7, 4, 3, 6, 8. Okay, so this is my partition. And what is the corresponding key sigma? So you see I have here 8 indices. The first, the fifth, and the seventh are identified. So I have 1 is equal to 5, is equal to 7. So my quotient graph, this is one vertex. Then I have a vertex which corresponds to 2 and 4. And then I have 3 separate ones corresponding to 3, to 6, and to 8. Okay, so what is now, what are the edges there? I mean, the edges are the images of the edges which I had here. So I have to go from 1 to 2, then I have to go from 2 to 3, from 3 to 4, this is here going back, then from 4 to 5, from 5 to 6, from 6 to 7, and from 7 to 8, and from 8 to 1 again. And now you see what I have here is a tree. I don't have leaves. And actually, maybe you also saw that I always went over one graph and then I went back again. So if I'm now writing down the position of the A's, so I'm going, I mean A1, A2, that's position 1. So if I multiply 8 of the A's, they have index I1, I2, the second one has index I2, I3. So I mean 1, 2, this is the 1, then from 2 to 3, this is 2, from 3 to 4, this is 3, this is 4, this is 5, this is 6, this is 7, and this is 8. And so you see that each of my variables A appears exactly twice. And you even see in this, I mean, going from here, this is A I1, I2, and going back is the other way around. It's exactly as we have in the Gaussian case, that we really, I mean, we have to pair Aij with Aji. Okay, this is really the leading order which shows up here. Okay, this is true in general. Good. Okay, so this corresponds to a tree, and if you now compare this partition sigma, so the sigma tells us what have I identified here, and the Preveras complement essentially corresponds to what is paired here on the edges. So maybe if you look on, what do I have here? 1, 2, 3, 4, 5, 6, 7, 8. Let me take here the A's, and then you see, I mean, 1, 2, and 3 are paired. So, and this is when I multiply my 8 entries of the matrices, then the second position is multiplied, shows up as the third, the first is the fourth, the fifth is the sixth, and the sixth is the eighth. Okay, and this guy, this is now the non-crossing pairing, which always show up in our usual formula, and of course this is connected to the sigma by the fact that the sigma is, okay, not the complement, but the inverse of the complement. So for the complement I'm putting numbers here, for the inverse I'm putting them on the other side. And then if you see, when I do the complement, I'm connecting here as much as possible without getting crossings. Then you see that this is exactly this one. So this is now one bar, 5 bar, and so on. Also I get 1, 5, 7, which is this block. I get here 2 and 4, which is this block, and then I have the other 3 single bars. Okay, so that's the general correspondence between those things. But this is always somehow a problem with summation over matrices. I mean, I have here the entries, and they are indexed by i's, but I can talk about the kernel of the i's, but of course what is interesting is actually the pairs of the i's showing up here. So I miss, in general considerations, I must go back and forth between both of them. So I have to compare partitions of the positions of my matrices with the partitions of the indices which appear there. And at least in the limit, this correspondence is given by the Bravera's complement. Good. Okay, and so this means that this summation here in the end is given by the non-crossing pairings, and for each of them this contribution is 1, if the second moment of mu is 1. So this means what we get here is really the moment of the sinusoid. So thus moment is asymptotically given by the number of non-crossing pairings of components. Good, okay, so maybe finally let me make a remark on how is our situation we are going over to the asymptotic freeness question, because that's really what we're interested in. I mean, this is classic random matrix theory. Actually, this was there from the very beginning. But now what we want to do, of course, is not take one Wigner matrix, but take independent Wigner matrices and ask, are they asymptotically free? Okay, and I mean, here you see that essentially if I take more, it's like in the Gaussian case, we are just putting an upper index here, which tells us which matrix we consider, and this does not really interfere with those arguments. Okay, so from this it's more or less clear that if I take independent Wigner matrices, they are asymptotically free, more or less by the same kind of proof. Okay, but the more interesting question is what happens if I'm adding diagonal, or if I'm adding deterministic matrices. And then of course the situation is getting a bit more complicated. I mean, first of all, if I'm restricting to diagonal deterministic matrices, then this will not really change the index structure. I mean, all the arguments here are about the index structure. Where are the indices the same, where are they different, and then I take also the conditions, the constraints which are given by independent entries of the Wigner matrices. But if I'm multiplying with an additional diagonal matrix, then of course I'm putting in general more indices there, and things are getting complicated. But if the deterministic matrices are diagonal, then this doesn't really make a difference. Also, I mean, in general, if I multiply my Wigner matrix with another diagonal matrix, I would have here full index. But if I say it's diagonal, then of course this here must be of this form, where this is the same as this, and then I continue here with the AI2 I3. And so this means on the A's I have the same structure as here, and the arguments still work. And then of course I should see what do I get in these. But the main arguments don't really pose a problem. Okay, so from this point of view, including diagonal deterministic matrices should also not make really big difference. But if I have a general deterministic matrix, then of course I have to multiply it here with I2, I3, and then I have here I3, I4, and so on. And now you see I have somehow lost this relation between the indices here and the indices here, which I used a lot there. And now things are getting more complicated. And it's not a priori clear that it works. Of course, in the Gaussian case it worked because we had the big formula and then we really could write down a nice formula. And now in this general case, it turns out that the result is still true, but actually the proof is annoyingly complicated. Okay, so I mean it's more or less clear to everybody that it should work in this case and it should be done, but if you really try to do it, it's much more complicated than you think. Okay, so I mean there exist now proofs. I mean there's one in the book of Anderson, Ione and Saitoni, and also in my book with Jamie, we have a proof of this. And I mean the idea was just to write down very quick a proof of this when we started this, because it should work without problems, but it turned out it's really complicated. And you have to use a lot of things. So like this from a combinatorial point of view, and I still hope maybe at some point we can find a nicer proof. So the statement is true, but I'm not really satisfied that the proof has to be so complicated. But anyhow, maybe I just want to give you the statement. I'm not a proof. Yeah, so here's the theorem of this. And I think this is important to know that has a statement like this, because in many concrete applications, I mean free probability is used in concrete, for example in wireless or something like this, and then it's very rarely that Gaussian random matrices are canonical input in your model. So it's much more realistic to have something like a Wigner matrix. And for this, it's good to know that actually also in this case, the result about asymptotic freeness are true. So that 1 up to P, let's say the probability members are. So we take now, we allow P Wigner matrices, and we allow that all of them have a different distribution. And of course, in our setting, we assume the existence of all moments, and the vanishing of the first moment. And I'm actually not sure how much one can generalize this in an analytic way. But anyway, so that's what we have here. And then we consider corresponding key Wigner matrices. Corresponding, and each of them should be n by n. Matrix, and of course AN1 should have the distribution U1 for its entries, AN2 the distribution U2 for its entries, and so on. And of course those matrices should be independent. And then in addition we also take diagonal matrices. Maybe there we also take a couple of them, too many. Assume that they have a limit distribution. Such that for distribution will converge the Q to a tuple of elements in a non-commutative probability space. It just means that all the joint moments of those guys have a limit if n goes to infinity. Good. Okay, and then we need an additional condition. I mean, in the calculations for mixed moments in the A's and the D's, there will be terms which we know will survive in the limit, and they give what we know from the free probability theory, but then there are other terms which have to go to zero, and I mean they will go to zero because they don't have so many contributions, but of course for this we have to control that their contribution in the terms of the D's, the moments of the D's, does not explode if n goes to infinity. So this means we need a kind of control on the D's, that they are not exploding if d goes to infinity in your operator. So that's what we also have to assume here, such that sup over the norm of my guys here. So I take the sup over all r's. Okay, that's just a final number, but then also over all n. So this means I can control, let's say, for each of those guys here, I can control the operator now if n goes to infinity. And that's what I need to control the terms in my calculation, which I have to check that they go to zero. Okay, so we have to assume that this is bounded. Okay, so the norms of those guys are not exploding. Good, and then the statement, of course, is, as you can expect, then, as n goes to infinity, we have that all my matrices together, so the A's, so A1 up to AT, and these, B1 up to EQ, converge in distribution to a tuple of S1, SP, and B1, EQ. Now, of course, the S's here are semicirculars, which are free, and those guys are free from the D's. Of course, the D's among themselves, they have exactly the distribution which I have more or less described here, but in addition now, I mean, they are getting free from the S's. So each SI is a semicircle distribution, and the main point is that S1 up to SP and the collection of the D's, D1 up to DQ, they are free. So the S's are free among themselves. Those guys are becoming asymptotically free, and they are becoming free from the D's. Of course, the D's are not free among themselves because I have described some joint distribution of them. But they are getting free from those guys. Okay, so in particular, the Wigner matrices and the deterministic matrices are asymptotically free. That's the same result as for G. But the proof of this is much more complicated. But at least it's done. Good. Okay, so now at the end, I want to show you some pictures of random matrix calculations. So, because I mean, we have now this relation between freeness and random matrices. So this essentially goes in two directions, and now I want to show you calculations which show that we have a powerful machinery for calculating eigenvalue distributions of random matrices in the limit. And the rest of the term will go essentially the other direction. So namely, show how we can use random matrices to get some ideas about the structure of Neumann matrices. Where free probability was invented in the context of the Neumann algebras. And I mean, up to now I have not talked about phenomenon algebras, but next week, on Wednesday, I will start to talk about this. Okay, but now I just want to show you what is machinery. I mean, we have this machinery of free convolution, so we can calculate the sum of free variables quite effectively. What this tells us about random matrices. Good. Okay, so let me start. Maybe first is presenting you a picture of two heroes. I mean, this is on the left, this is Wigner, and on the right is who introduced free probability theory. Good. But now, so what about, I mean, Wigner's semicircle law? That was the first main result about random matrices, and we only talked about the average situation. No? Okay. So this means if I'm looking, for example, on a 10 by 10 random matrix, I should not look on one of them, but I should average over all of them. Oh, okay. But so maybe here I have two of them. So if I take a 10 by 10 matrix and I'm looking on the 10 eigenvalues. So here I have plotted a histogram of the 10 eigenvalues. So this is one GUE matrix generated in a random way. So this means I'm generating in a random way with a Gaussian distribution the entries. 10 by 10 I get 10 eigenvalues sitting here, here, here. And then I do it another way and I get something here. And of course it's clear that this is not, has not much of a structure. But if our results say if I average over all of them and then n goes to infinity, I approach the semicircle. And I mean, I mentioned that actually there are stronger results which say that almost surely I get a semicircle, which means that each of those pictures, if n is getting large, itself looks like a semicircle. Right? So maybe I make the picture a bit bigger, so I'm taking now two 100 by 100 Gaussian random matrices. So this is one matrix, generated randomly, and this is another one. And now you see, I mean, the pictures look the same. What we have proved is essentially that if I average over all the pictures, of course there are infinitely many GUEs, if I average over all of them, then the pictures should be close to the semicircle. But this strengthening, which is true from the classical context and also for our asymptotic Freeness result, tells us that actually if I'm just looking on one typical matrix, it's close to the semicircle. So here, this is for 100, and then if I'm going to a 3000 by 3000 matrix, then it's more or less the semicircle. So these are the histogram of the 3000 eigenvalues of one GUE, and this of another one. Good, so that's about the semicircle. And maybe here it's again, so that's the classical theory. So we can be looking on the eigenvalues of a GUE matrix, and Wigner's theorem tells us that actually in the limit we get a very nice distribution, which is the semicircular distribution. And of course, I mean this fits our matrices. Okay, so that's classical random matrix theory. But now, I mean, what free probability allows us is to look on more complicated things. So in particular, not just one matrix, but maybe taking also sums of matrices. I mean, what we really can deal with is the sums of free things. And we know now there are many matrices which are asymptotically free. And maybe the first type of results which we had was that if I take a Gaussian random matrix and if I take a deterministic matrix, they are asymptotically free. So what I want to consider here is the sum of two such guys, an plus dn, and an is a GUE, and for dn, the deterministic one, I just take a diagonal matrix, because it doesn't matter, and I'm describing somehow this distribution of it, so that it has, okay, so this should be a diagonal matrix, and it should have a quarter of its diagonal elements, I mean, elements of the diagonal are the eigenvalues. A quarter of the eigenvalue is on 1, another quarter is on minus 1, and half of it is of minus 2. So I'm taking, you can say I'm taking this 4x4 matrix and I just repeat it as to fill up the matrix. Okay. And then, of course, we know those guys are asymptotically free. So the asymptotic distribution of this in the limit, maybe the limit, of course, so the distribution of dn, not only the limit, but for most of the n's, is given by this distribution. Also, it's a probability distribution mass 1 over 4 from +1, -1, and -1/1, 1/2 and -2. Okay, and now we can calculate the free convolution between the semicircle and this guy here. Okay, and this we can do, we have effective machineries, this we can do with our subordination iteration. Of course, we can also write down equations involving the R transform, but of course, I mean, for things like this, I mean, there are usually no ways of solving it. But we know we have this subordination formulation, which we can do. This is just numerical. I mean, that's what I have done in these pictures. So what we know is, I mean, if I have, so what I need of my distributions are essentially the Cauchy transform, or some version of this. So we have this H mu of Z. This was one of the Cauchy transform minus Z. And so what I need is the Cauchy transform, and the Cauchy transform of an atomic thing is something which we can write down very easily. I mean, the Cauchy transform of this UD here, so what is this? I mean, this is of course mass 1/4, and then the Cauchy transform is I integrate 1/Z minus T over my distribution, but this distribution here has atoms, so this is 1/Z plus 2, here is twice, plus 1/Z minus 1 plus 1/Z plus 2. So that's the Cauchy transform of this guy. I can write it down very easily. Of course, I would not like to take the inverse of this for solving for the R transform. I mean, the Cauchy transform is very easy, very nice. Okay, but I mean, for this iteration procedure, I don't need the R transform. I just need this here, which of course is as nice as this. And then we know that we just have to look on, we need the subordination function, because we know that here I want the Cauchy transform of a free convolution at some point. Then I can take the Cauchy transform of one of them, which I know, for example. And here I need the subordination function. And the subordination function I can get by iteration of the function which just involves these H functions of this guy. So this G set of W is Z plus H mu of Z plus H mu of W. So I need the Cauchy transform of both of them, but I mean I also have the Cauchy transform of the semicircle, for example. Okay. So I just have to iterate this here, starting somewhere in the upper half plane, and then iterate this. And how do I get this picture? Of course, if I have the Cauchy transform, then I should go to the real axis, and this converges to the distribution. So what I'm doing in this picture is here, I mean I take the set here as T plus I epsilon for small epsilon, and then I just do this procedure. I just iterate this, and this converges to something. And then if I'm very linear, I produce this picture. So this is just a subordination iteration. So we can really do this more or less for any given distribution. Good. Okay, so this is the subordination iteration. And then of course one can also calculate the eigenvalues of the corresponding matrix picture. And here again, I have taken a 3000 by 3000. And again, this is just one. I mean, our results would say you should average over the GUEs. Okay, but I mean, I can strengthen this, and it's really true asymptotically. So this means almost surely for one realization, I should be close to the result. So I have here the eigenvalues of a randomly generated GUE, and I'm adding this very specific diagonal matrix. And then this is the histogram of the 3000 eigenvalues, and I mean here, so this is the comparison of the two. So I mean, maybe are quite close to the result. Okay, and maybe we can also do more. So maybe this was the step where we had a GUE plus something. This something we could do arbitrarily, but we can do more. We can take the sum of two arbitrary things. Also by rotating one of them randomly. So what I'm doing here is I take now, let's say, the sum of two diagonal matrices, T1 and T2, but the second I rotate randomly. And the first T1, I mean, D1 and D2 are here not the same. One of them is the same as I had before, which was a diagonal, one was on the anyhow. So I take the diagonals which have this distribution. So D1 has it is there, eigenvalues of -2, -1, 1, and 2. Is the same matricity. And mu2, but mu2 has eigenvalues of plus and -1, and then a -2 with twice. So actually, the second 2 for the D2 should also be -2. Okay. But anyhow, it doesn't make a big difference. Okay, but so I'm taking here this, and so our results tell us that the eigenvalues of this matrix model should be approximated by the free convolution of mu1 and mu2. Okay, here I've calculated via sub-ordination iteration the free convolution of those guys. You see, I mean, those really can be wild objects. I mean, there's no hope that you can solve the corresponding equations which you get, let's say, from the R transform machine. But via subordination, I mean, subordination does not really care how complicated those things are, as long as you have a way of calculating the Cauchy transform. Good. Okay, so that's the free convolution of those two measures calculated via our subordination machinery. And here is the corresponding random matrix picture. So I've taken the D1 and D2 as diagonal matrices, where for D1 and D2 I just have spread those plus minus 1 and 2s along the diagonal, and then I have rotated the second one with a high unitary random matrix. So here I have also generated a 3000 by 3000 high unitary random matrix. But just one instance of this. And so I'm looking at this guy, and here's the log of the 3000 eigenvalues of this, and here's the comparison of the results. So I think this shows quite clearly that we have quite powerful analytic machinery for calculating sums of quite complicated random matrix models. Good. Okay, so that's about the random matrices and the asymptotic freeness. And next time, I will then start with talking about von Neumann algebras. So all this free probability theory was introduced in operator algebraic context, and by trying to attack some deep and still open questions of von Neumann algebras. Okay, and first I want to give you a very short introduction to von Neumann algebras, in particular from the point of view what we really are interested in. But then I will also show you that free probability allowed us to not solve really the final question, but really give us a lot of information about the specific von Neumann algebras which was not there before. Okay, and these results are essentially coming from the connection of von Neumann algebras and random matrices. Okay. Because I mean the von Neumann algebras we have are generated by free operators. Because freeness was introduced in this context. Okay, now this tells us that we can model free random variables, free operators by random matrices. And this gives somehow a different picture on these von Neumann algebras. So we can also think of von Neumann algebras as generated by random matrices, and then we have a better idea what we can do of random matrices with the von Neumann algebras. In particular, what we want to do is to cut big random matrices into smaller random matrices. And this corresponds to a compression of von Neumann algebras. Good, okay, but that's for next time, so I stop here for today.